In this screencast, we're going to talk about stoichiometric calculations. This is a really helpful map. One of the things I want you to notice is that we cannot go directly from grams of one thing to grams of another thing. And so what I mean by this is if you have a chemical reaction, A plus B goes to C, okay? And let's say you know how much A you have, and you need to figure out how much B that you need to react with A to form C. You just can't say, hey, look, I have 1 gram of A. I also need 1 gram of B. You need to figure this out based on the mole ratio. Now, let's talk about mole ratios for just a moment. If we were to look at a balanced equation, and let's say we like A plus B goes to 2D, the number here, right, is called the coefficient, okay? And that's what we use for our mole ratios. And we get these from, of course, the balanced equation. So we can't go directly from grams of one substance to grams of another substance. So instead, we need to go from grams to moles. Now, we've already done these calculations where we go from grams of substance A to moles of substance A. You're going to use the molar mass going this way. We're going to use coefficients of A and B from a balanced equation to figure out the moles of B, and then we use the molar mass of B to figure out the grams of substance B. Now, we can use this for a lot of things. We can use this to find out how much reactants we need. We can also use this to figure out how much of a product we're going to produce. So don't be misled by what's being asked. If we're asked about the product or the reactant, we can use this stoichiometry pattern for everything. So let's practice this. And so here's our question. How much carbon dioxide would be formed if 10 grams of C5H12 were completely burned in oxygen? So this is how I approach the problem. I say, okay, hey, look, I have 10 grams of C5H12. It's completely burned in oxygen, and I'm asked how much carbon dioxide. So I have my grams of C5H12, and I'm asked for how much carbon dioxide. Now, a lot of times this will say how much in grams, but if you hear much, how much like this, most of the time grams is what you're looking for. So I always like to think of this in kind of, particularly when I started, make a map to figure out how I go from grams of C5H12 to grams of carbon dioxide. So I'm going to make a map just like what we saw on the previous page, grams of C5H12, and I need to go to moles of C5H12. And then over here, I know what I'm looking for. I'm going to do this with a question mark, is CO2, okay? So I need to take that from moles of C5H12 to moles of CO2, and then go back up here to grams. Now we need to look at the tools that we need. So whenever you're moving up or down in this, you're always going to use the molar mass. So anytime you're heading vertically, it's going to be that molar mass or molecular weight. I'm going to use MM here and here, okay? And then when you're moving across, that's when you're going to use the mole ratio from the balanced equation. Now, we always want to really watch to make sure our units cancel out as well, because that's where you'll be able to find a lot of small mistakes if you make them. So we start with the value that we have. We have 10 grams of C5H12. We're going to come in here, and we are going from grams to moles. So we need to use the molar mass. So I've calculated the molar mass, and remember we do that using our periodic table, and it's 72.15 grams per mole. So if you need extra practice, this is a great time to practice making sure that you can also calculate the molar mass and get 72.15. Now, the next step we're going to do is we're going to go from moles of C5H12 here to moles of CO2. The way that we do this is we use the mole ratio from the balanced equation. Now, I need to go back and put C5H12 here and C5H12 here because that helps me keep up with these mole ratios. You'll notice that your grams cancel here. So our grams have canceled out, and we're interested in the mole ratios now. So the mole ratio for C5H12, when we look at this, we need to make sure that C5H12 is here in our denominator so that those C5H12s can cancel out. Now I look right here and I see there's no number there, so we understand that's 1 mole of C5H12. And then when I look at CO2 right here, I see there's 5 moles of CO2. Now, this step is really important, and you have to show this step because that's that moment where you change from one thing to another. And so now we're right here in the process, and we're going to go from moles of CO2 to grams of CO2. The molar mass here is 44.01 grams of CO2 per 1 mole of CO2. Okay, and we can see our moles of CO2 cancel. We're left with grams of CO2 here, which is what we were asked for in our problem, and that's what we're looking for there. So when you do this, there are lots of double checks. You need to make sure all your units cancel out, and if you're following along with your map, you should be able to go from grams to moles pretty easily. Now, what you're going to do is you're going to take 10, you're going to divide it by 72.15, multiply it by 5, and then multiply it by 44.01. Go ahead and try that now. And the number you should get is 30.4989 grams of CO2. But we know we always need to be watching for our significant figures. Go back to the numbers that you're given in the problem. We have 3 significant figures here. We need to have 3 significant figures here. We're going to look at this number to see if we need to round. We see that that number is greater than 5 or greater, so we're going to round to 30.5 grams of CO2. Okay. Now, in this instance, we were given a reactant and we were asked for a product, but I want you to remember, we could just have easily been given a product and asked for a reactant, or given one product and asked for the other product, or given a reactant and asked for the other reactant. So there's lots of ways that you can use stoichiometry to figure out how much that you make. Now, one of the things about chemical reactions is we don't always have exactly the same amount of things, okay? So, for example, I surprised myself. I was ready to move on to the next topic and forgot that I put in another problem. So if the screencast kind of stopped on you, you haven't missed anything. We're going to get to limiting reactants in just a second, but I wanted to work one more problem with you, and I completely overlooked it in my notes. So we're going to calculate the grams of NO produced when 1.5 moles of O2 reacts according to the following reaction. So we have the reaction here. Now, I want you to notice that you start with moles and you're asked to calculate the grams of NO. So we've got the moles of O2 and we're asked for the grams of NO. Now, in our map, we started with the grams of something, but that step has already been done for us. So normally we would have started and done a conversion from grams to moles here, but what's happened is this has already been done. And they've just given us our moles of O2. And so we can adjust our map. We can say, okay, hey, look, I can make adjustments. I'm going to go from my moles of O2, and I still know up here I need to find my grams of NO. So I'm going to go from moles of O2 to moles of NO using my mole ratio, and then convert from my moles of NO to my grams of NO using molar mass. And so we start with the number we're given. We're given 1.50 moles of O2, and we're going to follow along that diagram. We're going to use the mole ratio. So we look and we see we have 1 mole of O2 per 2 moles of NO. We find that our moles of O2 cancel, and we've got moles of NO, so we're right here. And then we're going to go from moles of NO to grams of NO. And so we're going to use the molar mass to do this. The molar mass is 30.01 grams of NO per mole of NO. And so when we do this math, we take 1.5, we multiply by 2, and then we multiply by 30.01. The number that we get in our calculator is 90.03 grams, but we're always going to double check our significant figures. We look up here, we see that's 3 significant figures. This also needs to be 3 significant figures, and so we're going to look at this number for rounding. It's 4 or less, so we're going to keep it as is and say the answer here is 90 grams. Now, that beautiful transition that I worked on before, I'm gonna do again. Sometimes we don't have exactly 1 mole of this and 1 mole of this. Sometimes we have, say, 1 mole of this, but only a half a mole of that, okay? And so the thing that we have the less of limits us. Now, this is called a limiting reactant. You are already familiar with limiting reactants. So, for example, let's say you want to make burgers, right? And for 1 burger, you need 1 bun, 1 patty, and 2 pieces of cheese. We like a really, really great cheeseburger, okay? And when you go to your cabinet or your kitchen, and you say, okay, I have 12 hamburger buns, I have 12 pieces of cheese, and I have 12 patties. Okay? According to this recipe here, where you need 1 bun, 1 patty, and 2 pieces of cheese, as you make hamburgers, you're going to run out of your cheese first, right? Because for every 1 hamburger bun, you're using 2 pieces of cheese. This would be called your limiting reactant. It's the reactant that limits you. It's the one that means you can't make any more, okay? And just like in chemistry, we can have a limiting reactant. So we can use balanced equations to help us with this. We kind of view this as our recipe, where we say, look, we have 2 moles of hydrogen gas for every 1 mole of oxygen gas, and that's going to produce 2 moles of water. Well, just like the pieces of cheese here, we are going to run out of H2 first if we have equal amounts of these things, okay? And so that would be called our limiting reactant. Now, we're not always going to have equal amounts. So as a chemist, when I design a reaction, I want to take into account what needs to be my limiting reactant. And just honestly, it's the thing that costs the most. So you want the chemical that costs the most to be your limiting reactant. And the thing that's cheaper, you want to have a really big excess of. Now, we can also look at this visually. So visually, what you can see here is hydrogen gas is white, and then oxygen gas is red. And so if we were looking at this visually, and we have 1, 2, 3, 4, 5, 6 molecules of oxygen gas, and 1, 2, 3, 4, 5, 6 molecules of hydrogen gas, we're going to use up those 6 molecules of hydrogen gas. They're going to pair with 1, 2, 3 molecules, right? And those are going to turn into water. And so you can see that here. We're going to have 1, 2, 3, 4, 5, 6 molecules of hydrogen gas, but we're going to have 3 molecules of O2 left over. So the one that runs out first here is H2, and that is our limiting reactant. And that's what limits the reaction. And then O2, we have plenty of that left over. And so we say, hey, look, that's an excess. Okay? Or we have excess of that. That's what's left over. So when we talk about limiting reactants, this is just the substance that is completely consumed in the chemical reaction. And it determines the amount of product that can be formed. During the reaction. Okay, it is identified by the number of moles of reactants, as well as the stoichiometry of the balanced equation. So these are some ways that we can identify this. So when we look at this in a limiting reactant example, okay, it says you've got SO3, sulfur trioxide, reacting with water, forming sulfuric acid. What's the limiting reactant when 20 grams of sulfur trioxide reacts with 10 grams of water? Now, this is really, really nice. It's asking you what the limiting reactant is, but sometimes it's not going to ask you what the limiting reactant is. Sometimes it's going to say, instead of what's the limiting reactant, sometimes it's going to say, right, how much H2SO4 can form when 20 grams of SO3 reacts with 10 grams of H2O. The context clue here that this is a limiting reactant example is you are going to be given 2 or more reactant amounts. This a lot of times is a sneaky question because it won't come out and say, what's my limiting reactant? So the process here is you need to figure out the one that produces the least, okay? So one of the ways to do this is to figure out, right, how many moles of products, and you can either do moles or mass, how many moles or grams of product are formed with each reactant. Okay, so we have to do stoichiometry, but we've got to do the stoichiometry calculations twice and then pick the smaller amount. Okay, so you're going to do stoichiometry 2 times once for each reactant. And then the limiting reactant produces the smallest amount of product. Okay, so we're going to work on this example. So for SO3, so we've got to do it for both. So for SO3, I'm going to do stoichiometry again. Now, once you get good at stoichiometry, you don't have to make a map every time. And so you can just kind of delve in and you can say, look, we've got 20 grams of SO3. I know I need to convert that to moles. And so I'm going to use molecular weight to do that. That's 80.06 grams of SO3 per mole of SO3. And then I am looking for the moles of sulfuric acid. Okay. And I can look here and I can see there's 1 mole of SO3 for every 1 mole of sulfuric acid. Just like that. And so when I look at this, I can now come in and say, all right, I'm going to pick up my calculator and I'm going to make 0.02498 moles of sulfuric acid with SO3. Now you need to do the exact same type of reaction with water. So now we're going to come here and we're going to look at water, and we're going to say, great, I have 10 grams of SO3. I know using my molar mass, 10 grams of water, H2O. I know using my molar mass that water is 18.02 grams per mole of water. And then I can go up and use my mole ratio to say, look, I have 1 mole of H2O for every 1 mole of H2SO4. Okay. You'll notice your units cancel, right? So our grams cancel here, our moles cancel here. We're left with moles of H2SO4. When you do this math, you get 0.05594 moles of H2SO4. Okay? Now, the question originally asked, what is our limiting reactant? The limiting reactant is going to be the one that makes the least amount of sulfuric acid. So SO3 here makes 0.02498 moles of sulfuric acid. H2O makes 0.05594 moles of sulfuric acid. So that means that SO3 here is our limiting reactant. It makes the least amount. That's the max amount that we can make with this reaction is 0.02498 moles. Okay? That means we're going to have water in excess. That's going to be our excess. So if I were to ask my second question, how much H2SO4 can form, you take the limiting reactant amount and you're going to convert that to grams. So we take 0.02498 moles of H2SO4, and I use the molecular weight here, which is 98.079 grams per mole for sulfuric acid, and that gives me 2.450013 grams of sulfuric acid. Now, again, we need to think about our sig figs. When you look at the original problem had 4 sig figs. So that would be this number. We look here to see how we have to round. So it'd be 2.5450 grams of sulfuric acid. Okay? And so this is how we do limiting reactant problems. Let's do one other example. So if 10 grams of methane is burned with 20 grams of oxygen to produce carbon dioxide and water, what's the limiting reactant? Now, your first step here, well, I want you to notice a few things. One is, again, this is just really, really nice. It's asking you for the limiting reactant. But I want you to notice you've got 1 amount of a reactant here and 1 amount of a reactant here. 2 reactants. And it's asking you how much you're going to produce, or it's asking you what your limiting reactant is, but that's your context clue that this is a limiting reactant problem. The other thing I want you to notice is, to solve these problems, you have to have a balanced equation. So we have to come in here and write the equation like we did earlier in this chapter, but also balance it too. So we're going to come here and we're going to say, great, I see we got methane, CH4, is burned in oxygen, plus O2 to produce, remember produce is that context clue that we're going to have products now, CO2 and water. Now we need to balance this. This is one we've balanced before, but you would need to balance this, say, on the test or for your homework. And so this is now a balanced equation. Bonus points if you've identified this. You should also be able to identify this equation. This is a combustion equation. And so we're going to start with methane, CH4. And we're going to figure out how much methane, how many moles of methane that we need to make. And so, how many moles of water or carbon dioxide we're going to make. So here's the deal. It doesn't specifically ask for either carbon dioxide or water. So you can pick whichever one. It doesn't matter. I'm going to pick CO2. So I'm going to go from CH4, which is 10 grams of CH4. I'm going to convert that to moles. And then I'm going to convert that to CO2. Now, if you want to do this with water, that's fine. Your numbers will be a little different, but you still should get the same thing as the limiting reactant, okay? So I look at my mole ratio. I see for every 1 mole of CH4, I have 1 mole of CO2, okay? I notice my moles of CH4 cancel. My grams of CH4 cancel, and I'm left with moles of CO2. So when I do this math, I have 0.0623 moles of CO2. Okay. Now, I'm also going to look at O2. I'm starting with 20 grams of O2. I know that my molar mass of O2 is 31.99 grams of O2 per mole of O2. And then I look at my my mole ratio, and I know I have 2 moles of O2 per every 1 mole of CO2. When I look at this and I do my math, I see I have 0.3125 moles of CO2. Now, if there was a little pause there, it's because I caught a mistake and I needed to pick up my calculator and do it again. I wrote this number's wrong. It should have been 0.623 moles of CO2. So if you didn't miss anything, if you heard a little jump, but I did what I had was not the same as my notes, so I wanted to double check that. All right, so now we have both our moles of CO2 that we would produce with methane and our moles of CO2 we would produce with O2. The one that produces the least amount is our limiting reactant. So when we compare these, we've got 0.3125 moles of CO2 here and 0.623 moles of CO2 here. We make less CO2 with our O2. That means our O2 is our limiting reactant, and this is the max we can make. Okay. Now, if you want a little extra practice, you can figure out how many grams of CO2 you would make. You would just start with the moles of the limiting reactant and convert that to grams.